Welcome back to Analog Electronics. Today is lecture 36 and we are going to continue with our discussion on power amplifiers. Yesterday we were talking about power amplifiers and we had a few revealing insights. We started with the common source amplifier and made it as simple as possible with a big inductor and a big capacitor, right. We also worked with a common drain amplifier, where the same thing happened. We had a big inductor and a big capacitor. Then we applied an input, looked at the output, and then we figured out the ratio of the power that we managed to deliver to the load to the power that we absorbed from the DC power source. And we found that there is an upper bound on this ratio. The upper bound is 50% and that too this is an optimistic, overly optimistic upper bound, right. We already discussed the lacuna, why this even this 50% is little overly optimistic. Anyway, so let us say best case scenario is 50%. So, 50% is the efficiency of the circuit, the ratio between the power that we can deliver to the load to the power that we absorb from the DC power source, which effectively means that if I want to deliver 1 watt to the load, 1 watt is going to be burnt extra as heat. Okay. And this is generally a very bad thing. I mean, you do not want to waste power as heat. Heat is the worst form of energy, right. So, once energy is burnt as heat, you can't get it back, you can't, it is mostly not usable anymore. All right. So, our circuit we had, I will just redraw once again. We had one MOSFET, we had an input and we had a big capacitor at the output. The biasing was through the inductor. Okay. So, this is the structure of the circuit, all right, and more or less this configuration is the configuration of a power amplifier. Okay. We also discussed an alternate version of this, where the MOSFET is common drain as opposed to common source. The common drain form is sometimes used, but it has other issues, namely, you remember we had discussed a long time back when we were studying the common gate, common source, common drain amplifiers. After we had done the capacitive stuff, after figuring out the capacitances, we were redoing the common source, common gate and common drain circuits, right. Now, during that revision of the common drain circuit, we figured out that the output impedance of the common drain circuit is inductive. It looks like an inductor, okay, which basically means that as frequency increases, the output impedance increases. Now, this is true for all voltage buffers. Okay. Anyway, so we were seeing that if there is capacitance in the load, then the inductive output impedance and the capacitance in the load resonate with each other and it can cause instability. Okay. A lot of times, therefore, the common drain circuit is not going to be preferred, right, especially if you know beforehand that the load is capacitive. If the load is not capacitive, if you are sure there is no capacitance in the load, then no problem, but if the load is capacitive, then beware, right. You can still use common drain circuit as long as you know what you are doing. Okay. So, you should convince yourself before jumping into the common drain circuit. Convince yourself that this is going to work without causing instability. Instability means when there is resonance in the circuit, then somehow the poles might end up in the right half plane, and then you are going to get large oscillations. So, you might see these things in the lab a lot of times. For example, a lot of times in the lab, when you are trying to draw a large current from a power supply. Okay. There are these power supply boxes, right, in the lab. All of you have gone to the lab, have used some lab or the other, and typical equipment in the lab are there are oscilloscopes, there are power supplies, there are function generators, right. And a lot of times the power supply is either going to look like a box like this or a box like this, something where you connect, right. Now, when a lot of times when you try to draw large impulsive currents or large currents, okay, transient currents, large transient currents. Okay. Suppose I try to draw a current waveform which is this is outside the boundary of this course, right. So, I am just discussing sketchily. Suppose you have got this power supply box, and from the power supply box you are trying to draw a current that looks like this. Okay. And this amplitude is very large, and this time also is very small. All right. And invariably what happens is that loads are capacitive. Okay. Remember, recollect your class 11 or class 12 electrostatics. When you studied electrostatics in class 12, you would have studied that a metallic sphere has some capacitance. Okay. Just a metallic sphere has capacitance. Okay. Anything made up of metal has capacitance. Okay. Capacitance is everywhere. Between any two objects there is some capacitance. You can work it out as if conductor, insulator, conductor, there is capacitance between my two hands. Okay. So, these capacitances are there everywhere. It does not really have to be a physical capacitor. Okay. You have implemented something on a circuit board. Now, there is a wire going to the circuit board, there is another wire coming out of the circuit board. Between the two wires there is going to be capacitance. Okay. So, invariably, even if you did not deliberately have a capacitive load, invariably your load will have some form of capacitance, a little bit of capacitance, okay, if not a lot. So, for example, in the lab we have measured that if you take one of those integrated circuits, the capacitance between any two pins is of the order of several picofarads. Okay. So, capacitance is there everywhere. Now, suppose you take this large current, transient current, you draw this transient current from the power supply. The power supply is a voltage buffer of sorts. We are going to discuss power supplies soon, but it is a voltage buffer of sorts. Its output impedance is going to be heavily inductive, and you are driving some sort of a capacitive load. You have got a heavy inductive output impedance, right. If you look at the overall Thevenin equivalent impedance, you will have one inductor, one capacitor, right, and you have this large transient waveform. It is going to cause a huge amount of. So, you are going to have poles which are a pair of poles which are very close to the imaginary axis, if not on the right half plane. Sometimes these poles go to the right half plane, then it is disaster. Even if they do not go to the right half plane, if they are close enough to the imaginary axis, you are going to get a response that looks like this. okay, if you have got a pair of poles very close to the imaginary axis. Okay, and whenever you have got this L and C coming in shunt with each other, right, this is something to be afraid of. All right. So, generally speaking, therefore, we avoid this kind of a setup, especially when it comes to power amplification. However, the concept is the same, okay, and we discussed it in the last lecture. The result is exactly the same, just that in the last class we did not incorporate capacitance between gate and source, right. If you throw in capacitance, then poles are going to pop up, and then suddenly you might start observing that things might become unstable or near unstable, both are bad enough. Okay. So, generally speaking, this is avoidable unless you know what you are doing, right. A lot of times if you really know what you are doing, then this is okay. All right. So, our power amplifier circuit for now is going to be the first one. We are going to stick to this power amplifier circuit, and even with this power amplifier circuit, what you saw was that if I want to maintain the MOSFET in saturation at all times, then the maximum theoretical upper bound of efficiency is 50%. Fine. So, this kind of a power amplifier is called a class A power amplifier. Okay. And in the class A power amplifier, the MOSFET is in saturation all the time throughout the cycle of the waveform. So, the cycle of the waveform if you think of one sine wave, right, throughout this one sine wave, this current waveform is going to. So, if the voltage over here is this, then the current is the opposite. So, throughout this waveform the current is positive, non-zero, right. At best it is hitting 0, right, but it is not going below 0 throughout the waveform. So, we say that the MOSFET is conducting current through all 360 degrees of the current phase of the signal, right. The entire period of the signal, the MOSFET is conducting current, right. We say that the MOSFET is conducting current for all 360 degrees of the phase of the signal. Okay. And in this case we found that the maximum efficiency is 50%. All right. Now, when I phrase it like this, it kind of gives you a hint as to what to do next. Okay. So, the hint is that we are going to keep the MOSFET conducting for all 360 degrees. Okay, that is going to be the hint, right. So, if not 360, how many degrees? We are going to try different options. Okay. So, let us try the following. So, our circuit remains the same. Okay, this is the circuit. For all the power amplifiers, the circuit is the same. Only later on we are going to make some slight modification and arrive at newer circuits, but right now the circuit is fixed. All right. We are going to make some slight tweakings over here. What we are going to tweak is the value of VGS, capital VGS. Okay, we are going to change the value of capital VGS. So, yesterday we called this V in or VG. I think we called it VGS or VGS. Okay, it does not matter. Okay. What we are going to tweak right now is this one. So, earlier the combined gate voltage of the two so if you look at the combined gate voltage of the two, it has some value and around the value you are going up and down. Okay. And earlier what was happening was the minimum value as well as the maximum value, this entire range of values would be above the threshold voltage of the MOSFET, such that there is current through the MOSFET all the time. Fine. This was the strategy earlier. Earlier my value of capital VGS, which is capital VGS, this center line is capital VGS. Okay. Small VGS is the amplitude around that. Okay. The net waveform is small v sub capital GS. Okay, the combined waveform is small v sub capital GS. Now, earlier we were making sure that the MOSFET always conducts current no matter what. Okay, what does that mean? That means that small v sub capital GS is more than a certain threshold all the time, Vt of the device all the time through all 360 degrees of the signal phase, right. This is what we were looking at earlier. Now, let us stop doing that. Okay. Let us cut the MOSFET off for part of the duration. Let us cut it off. So, what are we going to do? We are going to reduce the value of VGS to a point. So, earlier my current waveform okay. First let me draw my earlier current waveform. Earlier the current waveform was like this. I had some value and around the value I was going up and down like a sine wave, and I was making sure that I do not go below 0. Fine. Now, what we are going to say is, let us cut the MOSFET off for some part of the cycle. Let us not keep it on throughout. Okay. So, we are cutting the MOSFET off. Let us say we cut it off for half of the time. So, we are going to conduct only during this time and keep the MOSFET off the remaining time. Let us say that is the plan. Then I am going to make a current waveform that maybe looks like this. I am sorry. So, this was the earlier current waveform. Now, the new current waveform would look like this. Is this okay? Fine. This is going to be the shape of the current waveform. Now, this is small I sub capital D. All right, let us formalize it. Let us say small I sub capital D, this is time t equal to 0. Let us say this is pi, this is 2 pi, 3 pi, and so on. Okay. So, small I sub capital D is equal to sum I naught times sine. So, let us without any loss in generality, let us call this theta instead of time. Okay. I am just changing the alphabet over there. Okay, something like this. So, let us say I naught sin theta is the current. So, this current has a peak of I naught, peak value of capital I naught, all right, and between 0 and pi it follows I naught sin theta, and between pi and 2 pi it follows 0. Again between 2 pi and 3 pi it follows I naught sin theta, again 3 pi and 4 pi it will be 0, and so on and so forth. All right. And how did this happen? This happened just by reducing the value of the gate bias voltage VGS. Okay. So, this is what we have done. Now, the inductor is a short circuit, it is so big that it is a short circuit for DC and a completely open circuit for AC. Okay. What does that mean? This current is still capital ID, all right, and this current is still small I sub capital small I small d. Okay. This is true no matter what. It does not matter what is the waveform of small I capital D, this relationship is true. The DC part is going to come through the inductor because it is an AC open circuit, and the AC part is going to come through the capacitor because it is a short circuit for AC. All right. So, this is true no matter what. Now, how will you split up small I d into a DC part and an incremental part? The DC part is easy, you just find out the average. Okay. What is the average current when the function looks like this? It is periodic, right. How do you find the average? Some of you will rattle this out already, because this is like a half wave rectified sine wave, right. If you do not remember how to do it, this is how you do it. You integrate and then you divide by the total time, right. The total time is 2 pi and you integrate and you divide by 2 pi. This is the average. Okay. And 0 to 2 pi, if I want to integrate from pi to 2 pi, it is 0 anyway. So, we do not have to bother, we just have to integrate from 0 to pi, and that too we have to integrate I naught sin theta d theta from 0 to pi, okay, and pi to 2 pi is 0 anyway. So, it does not matter. Integral of sin theta is minus cos theta, okay, and if I plug in cos theta equal to pi, I get minus 1, and if I plug in cos theta equal to 0, I get another minus 1. So, net is minus 2 over here, there was a minus sign up front, and therefore, the final answer is I naught by pi. Okay. And if you remember your half wave rectifier, then you have a voltage, right, voltage of 220 volts, you half wave rectify it, what do you get? You get 220 divided by pi. Okay. Anyway, so this is the result. All right. So, now what we have figured out is the DC part. So, small I d must be the rest, right. If I subtract the DC part out of the signal, then I get the incremental part. All right. So, small I d must be small I sub capital D minus capital I d. So, what is my small I d? Something like this. Fine. If you draw the waveform, then small I d, I am sorry, this is how small I d looks like. This shift is right, and this distance is I naught. So far so good, great. Now, this small I d does not resemble a sine wave at all. I mean it looks like a sine wave for only half the cycle. If you look at this is a periodic signal, you can look at the Fourier series of this periodic signal, you will get a sine wave component at the fundamental, but it will have harmonics, lots of harmonics. So, I am going to place the load over here in the circuit, okay. But before I place the load, let us think a little bit, right. Is it right to place just a resistive load over there, because small I d is going to come through that resistive load and it is not going to look like a sine wave at all, the voltage is not going to look like a sine wave, okay, and that is not something very nice. Instead, what a lot of people do is place a filter, okay. You can easily place a filter, let us say a notch filter, to make sure that none of the harmonics go through. So, you can have notch filter at the second harmonic, third harmonic, at all the harmonics, or you could place a low pass filter over there to make sure that none of the higher frequencies go through at all, right. So, there are a variety of techniques. Let us imagine that there is some sort of a filter like that, maybe that filter looks like this. Okay. So, imagine this current has components at the fundamental and at the harmonics. Alright, it has components at the fundamental and at the harmonics. As far as the harmonics are concerned, or let us say second harmonic is the dominant harmonic and you do not want to worry about the other ones. Okay. So, at the second harmonic I make sure L and C together form a short circuit. This is j omega L and this is 1 by j omega C, which can be adjusted in value, right. If this is some 5 times j, then this could be adjusted, C could be adjusted to be minus 5 times j exactly at that frequency, and as a result the net impedance of these two can be made to be 0, which means that the second harmonic is going to go through this, okay, because that is a short circuit. So, for the second harmonic it is going to go through this, right. Likewise, you can build a short circuit at third harmonic, a fourth harmonic, whatever, whichever harmonics you are worried about. Okay. So, we are not going to discuss this in detail at all. In fact, we are not going to discuss it at all. I am just trying to say that you can always conceive a filter that looks like that and place it over there. All right. And as you see, it is not terribly difficult to do that. Fine. Then what happens to the current over here that comes through the load? All the harmonic currents are going to come through this, through the short circuits, right, and the load can carry the current which is the fundamental of this periodic waveform. So, pause. Let us pause a bit. So, this is my ID, this is my small ID, okay. Small ID equal to something between 0 to pi, small ID is something else between pi and 2 pi. This is a periodic signal, right. What happens between 0 and 2 pi, this is going to repeat forever, okay, between 2 pi and 4 pi, 4 pi and 6 pi and so on and so forth, it is repeating itself. So, this is a periodic current. This periodic current can be broken up as a Fourier series. You know how to do Fourier series, right. Any periodic waveform can be broken up. For example, ID of t, I know ID of t is periodic, okay. Here I am writing t, but it is actually just theta, t is the same as theta for me. ID of t is periodic, I know, right. ID of t can be written as some constant plus, in our case the constant is already 0, we have already taken out the DC part, okay. In fact, you could have worked directly with I sub capital D of t, in which case this would be I naught by pi plus some a n sin plus b n cosine and these have to be summed from n equal to zero to infinity. You have all these components, I am sorry, not 0, n equal to 1 to infinity, Okay, the 0th term has already come out. Fine. This is the Fourier series. Now, in our case capital T is 2 pi, small t is theta. So, we have a little simplification over here. This is just theta, capital T is 2 pi. So, these cancel out. Okay. Just for clarity, I am rewriting. And do you know how to figure out the coefficients small a n and small b n? That is what you learnt in your maths class, in your Fourier series class, right. And as far as I remember, a n was given in the maths class as 2 by capital T integral from 0 to capital T x of t I am sorry, this was sine, a n this was sine, and b n this was cos. So, for the cos term you have to do a cos, for the sine term you have to do a sine, okay, an integral with the sine. This is what I remember from the Fourier series maths class. All right. Now, in our case, in our specific case, once again capital T is 2 pi. So, these two cancel out. This becomes 1 by pi. T is nothing but theta. Okay. And for now, I am really interested in the fundamental component that actually goes out through the load, which means that I am really interested in n equal to 1, okay, just the fundamental of this Fourier series is what is most interesting to me. All the other harmonics are garbage, right. I do not like these harmonics, I am not interested in them. I am interested in the fundamental. Why? Because my input voltage was at the fundamental, right. I made the sound at the fundamental. I expect the loudspeaker to respond at the fundamental. So, I am interested only in the fundamental. The garbage is not very interesting to me. So, I am interested in n equal to 1. Okay. And we have already taken out the DC component. So, whether you use small I sub capital D or whether you use small I sub small d, it is up to you, you will get the same answer. Okay. So, let us just do it. I am interested only in A 1, 1 by pi integral 0 to 2 pi. I d of theta small I sub capital D was a neater function. Okay. It looks more attractive than small I small d. So, let me just use small I sub capital D. Okay. I think my answer is going to come faster if I use small I sub capital D. The result is going to be the same. You can use small I sub small d as well. and if you remember, small I sub capital D is I naught sin theta from 0 to pi, and the rest of the time it is just 0, which means this integral you do not have to go all the way from 0 to 2 pi. From pi to 2 pi, small I d is already 0. So, the product of 0 with something else is 0, and the sum of all of that is going to be a big 0. So, therefore, you just have to deal with 0 to pi, and in that 0 to pi range, small I sub capital D is nothing but I naught sin theta. Times another sin theta, okay, and sin squared theta can be broken up into 1 minus cos of 2 theta, half of that. Okay. This is cos squared plus sin squared, and this is cos squared minus sin squared. So, the cos squared portion cancelled out, sin squared and minus of minus sin squared, 2 sin squared, half of that sin squared, just to check that this is correct. Okay. Then what happens? You can do integral of cos 2 theta d theta, right, from 0 to pi. What are you going to get? You need to replace, substitute 2 theta bit with some alpha, right, and then suddenly you are going to integrate from 0 to 2 pi, right, to double the frequency, which basically means that this the second half of the integral is going to be a 0, and therefore, you need not do it. You only have to work out the first half of the integral, which is an integral of 1, and therefore, the answer is just pi by 2 coming out of this. Okay. So, this is our result, and then there is A 2 and then A 3 and so on. What about B 1? B 1 is also at the fundamental. So, you need to check B 1 as well. Okay. And ID of theta from pi to 2 pi is all 0. So, once again you knock that out. Okay. Sin theta cos theta is actually half of sin 2 theta. Fine, and then again you substitute, you say let us make 2 theta equal to some alpha, then theta is alpha by 2, okay, and the integrals are going to be from when alpha is equal to 0 to when alpha is going to be equal to, alpha is 2 times theta. So, 2 pi, and if I integrate sin alpha from 0 to 2 pi, right, do not worry about this factor of half. If I integrate sin theta from 0 to 2 theta, then I get a big 0. So, this entire result is 0. So, B 1 is a clean 0. all right, and then B2, B3 etc. can be worked out, but we are not interested in B2, B3. We are only interested in A1 and B1, which means that the current that I am going to bring through the load. Remember, I have shorted out all the higher order harmonics. Okay, so, the higher order harmonics are not going to bother me. The actual current that is going to come through the load is just I naught by 2. So, I naught by 2 is A1, okay. A1 sin 1 times theta. So, it is A1 is I naught by 2, I naught by 2 sin theta is the current. Is this fine? This is clear? I hope this is absolutely clear. So far so good. We have not yet done any electronics. We have only kind of separated the current. We have split up the current small I sub capital D into a DC part, higher order harmonics and a fundamental. Okay. And I have figured out that if the current waveform looks like this, if it only goes from 0 to pi, that is, if conduction happens only for 180 degrees and not all 360 degrees, if it happens only for 180 degrees, then the DC part is I naught by pi and the fundamental is I naught by 2. Okay. The amplitude of the fundamental is capital I naught by 2, the DC part is I naught by pi. This is all that I have figured out so far. So far so good. Now, let us look at the voltages. So, when I do the voltages, this current is going to come through the load, right. If you think of the load as a resistive load, then the voltage is going to dip by this resistance times the current, right. So, the voltage over here, the signal voltage over here actually looks like a sine wave. Okay. So, the voltage at the drain is also split up into a DC. This is the DC plus the signal small v sub capital D, and this is only the incremental part small v d. Now, this small v d actually looks like a sine wave, right. Why? Because the sine current is coming through a load. Fine. You can always think of the load as a pure resistor. Even if it is not a pure resistor, even then it is a sine wave, right, in the steady state. So, this voltage over here is a sine wave. In that case, what is the maximum amplitude of this voltage? So, what is small v sub capital D? Small v sub capital D looks exactly like before. It is a voltage riding on top of VDD, some sine wave which is riding on top of VDD. So, the voltage at the drain okay. Maybe my phase is incorrect, right. If the current goes up, the voltage should go down. Okay. This is probably the correct one, ignore the black line. All right. This is how small v sub capital D is going to look. All right. And now, tell me what is the best case amplitude of this voltage. the amplitude has got to be VDD, right. So, this amplitude has got to be equal to VDD. So, the best case amplitude of the voltage waveform is VDD. Fine. Okay. Now, let us do some numbers. Okay. What is the current drawn from the power supply? ID, DC, it is a pure DC current ID. So, the power drawn from the power supply is VDD times ID. And ID is capital I naught by pi. Then what is the power delivered to the load? The voltage across the load is small Vd, sine wave. The current through the load is I naught by 2 sin theta, that is also a sine wave. Therefore, the power delivered to the load, this is you ignore the sin theta over here part, right. The amplitude is I naught, capital I naught by 2. This has an amplitude of small Vd. Therefore, the power that is delivered to the load is small Vd times the amplitude of the current, capital I naught by 2 divided by 2. Okay. And the best case, the largest amplitude of Vd is what we figured out is capital VDD. All right. So, the best case efficiency, the best possible efficiency is when this is largest. Fine. And all these factors cancel out very nicely, and you get pi by 4. All right. Any idea what pi by 4 is like? Pi is something like 3. Okay. So, 75, little bit more than 75, you get about 78%, 3.14 divided by 4, right, 0.78 approximately. Now, what is this? What is 78%? 78% is my new efficiency, right. It is the efficiency if I conduct the MOSFET only for 180 degrees out of the full 360 degrees, right. If I say that, let me restrict myself to just half of the cycle, right, and during that half of the cycle current goes through the MOSFET, remaining half of the cycle MOSFET is off, right, cut off, completely cut off because of gate bias. Then the best case efficiency in a scenario where the amplitude of the voltage is maximum, right. This is also an overestimate, right, overly optimistic, because this can't go all the way down to 0, right. But even then, even with an overly optimistic view, I get at least I get 78%, I am not stuck to 50%. Fine. All right, great. So, this kind of an amplifier, I have not done anything as far as the circuit is concerned. The circuit is the same. All that I have done is tweaked VGS, to a point such that half of the time the MOSFET is cut off. Alright. So, such a scenario is called a class B power amplifier, and here the MOS is in saturation. Saturation is wrong, is conducting, right. And let us not call it 360 degrees, let us call it 2 pi. Okay. Radians. So, in the class B power amplifier, the MOSFET is conducting for pi radians, and here the maximum efficiency is of the order of 78%, it is actually pi by 4, and that is the theoretical maximum efficiency. Okay. So, nothing much has been done. We have studied two kinds of amplifiers, power amplifiers, the class A power amplifier, the class B power amplifier, and in the next lecture we will study a few more. Okay. Thank you.